The universe is glitching. Why the fundamental code of reality is breaking down. The number on the screen wouldn't settle. 67 here, 73 there. Same universe, two clocks, no agreement. In a windowless control room, a researcher stared at a plot that said the cosmos expands at two different speeds. If that's true, the scaffolding of modern cosmology buckles. If constants drift, atoms fail. If atoms fail, reality tears. Meanwhile, something else was happening. Whispers that other sacred numbers were wobbling too. The lab went quiet. One detail would prove crucial later. To understand why this disagreement is terrifying, we need to go back to a century-old yardstick, a new generation of instruments, and a number that wouldn't behave. The number that wouldn't behave, the Hubble tension. Start with the stakes. Two gold standard methods weigh the same universe and hand back different answers. Not close enough, not within error. Different. On one side, the late universe distance ladder, Cepheid variables pulsing in nearby galaxies, Type Ia supernovae blazing like standard candles farther out. On the other, the baby echo of the cosmos, the cosmic microwave background, patterned by sound waves frozen when the universe was 380,000 years old. Both are precise. Both are careful, and they don't agree. From the latter's perspective, it's straightforward. You calibrate brightness. First, Cepheids, stars that brighten and dim with a steady rhythm. Their period tells you their true luminosity. You check that against parallax measurements, tiny apparent shifts in position as Earth orbits the Sun, so the 0 point isn't guesswork. Then you climb. Cepheids live in galaxies that later host Type Ia supernovae. Those supernovae explode with a well-behaved peak brightness once you standardize them. Suddenly, you have yardsticks reaching deep into the late universe. Compare distances to redshifts, and you get a Hubble constant around 73 kilometers per second per megaparsec. It sounds clean. It wasn't. Dust can redden light, metallicity. The chemical richness of a star can tweak the Cepheid period, luminosity relation. Some teams argued that crowding in dense star fields made Cepheids look brighter than they are. So they ran audits, new filters in the infrared to cut through dust, sharper imaging with Hubble, and then Webb to separate stars that blur together, independent anchors like the tip of the red giant branch to cross-check the 0 point. Each time they knocked down a systematic, the number stayed high. The ladder kept landing near 73. Meanwhile, the early universe told a different story. The Planck satellite mapped the CMB in exquisite detail, reading the acoustic peaks, the ripples set by sound waves in the primordial plasma. Those peak positions depend on the sound horizon, the distance a pressure wave could travel before light decoupled from matter. Feed that physics-heavy snapshot into the standard cosmological model, matter density, dark energy, baryons, neutrinos, and you infer a Hubble constant around 67. The inference isn't a direct measurement. It's model-dependent, but the model has nailed a lot of other things, from element abundances to large-scale structure. Here's where it gets tangled. Parameters in the early universe fit are entangled. Change the assumed helium fraction or the number of relativistic species and the inferred expansion rate shifts. Priors matter. So teams pushed. Vary the model, widen the priors, let extra neutrino-like radiation in, relax assumptions about spatial curvature. Each test moved the needle a little, but the core result held up. The early universe inference stayed low. You can feel the tension in the room when results land. Latter proponents point to multiple independent rungs, Cepheids, red giant branch tips, masers in galaxy disks, strong lens time delays, even gravitational wave standard Sirens beginning to weigh in. Early universe proponents counter with the internal consistency of the CMB and baryon acoustic oscillations that stitch the early and late universe together through the sound horizon. Both sides have citations. Both sides bring receipts. Then new eyes join the fight. The James Webb Space Telescope, with infrared vision and finer resolution, reobserved Cepheid fields that Hubble had charted. If crowding and dust were secretly biasing the latter, Webb should reveal it. Some teams saw Webb reinforce the higher age, once more near 73. Others, using alternative rungs like the red giant branch without Cepheids, landed closer to 70 and argued that within uncertainties the crisis softens. It didn't dissolve, it got sharper. Several groups now agree on this much. It's hard to push the ladder all the way down to 67 without inventing new problems. Meanwhile, gravitational lensing added drama. Time delays between multiple images of a single quasar let you solve for distances without standard candles. Those analyses, with careful modeling of the lens galaxies, have tended to favor higher H values, though their systematics, mass profiles, line-of-sight structure, are notorious. A multiply-image type Ia supernova, measured with Webb, offered a new route and also leaned high. The pattern is frustrating. Late universe, direct-ish methods are clustered high. Early universe, model-tuned inferences are clustered low. What nobody knew at the time, this wasn't just about one number. In parallel, a quieter debate over structure growth, how clumpy matter becomes over time, started to hum. Weak lensing surveys whispered that the universe might be slightly less clumpy than Planck's model predicts. Another small crack in the paint. Separate, connected. The argument spilled into conferences and Slack channels. Here's the human part. Imagine months of calibration checks, blinking through star fields at 2 a.m., trying to decide whether a single Cepheid's profile is contaminated by a neighbor faintly bleeding into the pixel. A postdoc flags a metallicity correction that wasn't applied consistently in a subset. The team reruns the entire pipeline. The answer moves by 0.3. Not enough. The tension lives. Stakes again because they're the heartbeat. If the latter is right, the early universe model is missing something. A tweak around recombination, maybe energy that briefly flared and faded. If the early universe inference is right, then dozens of clever distance tricks are all biased in the same direction. Either way, our confidence in the rulebook takes a hit. This was the moment everything changed. New data didn't collapse the disagreement, it framed it. The universe wasn't going to hand us a neat compromise. While expansion fractured, another number began to whisper, one that controls the way light and matter talk. The fine structure constant's quiet drift. While the expansion rate argued in public, a softer rumor passed hand to hand. Alpha might be drifting. Not a dramatic lurch, just a quiet wobble in the fine structure constant, the number that tells you how strongly light couples to charged particles. Alpha lives inside every spectrum line, every chemical bond, every star's heart. Move it a hair and the universe breathes differently. That's why the whisper mattered. To chase it, astronomers turned quasars into time machines. Light leaves a quasar when the universe is young, threads through clouds of gas, and those atoms stamp the beam with absorption lines, thin notches at very specific wavelengths. If alpha in that ancient cloud was slightly different, the spacing between certain lines shifts. Compare the pattern to today's lab values and you read a tiny change across billions of years. The method that unlocked sensitivity was called the many-multiplet technique, and it did something clever. Instead of tracking one line, S-drift, it compared a whole family of transitions from different ions, each with a different sensitivity to alpha. By taking a weighted chorus instead of a solo, you amplify the signal. Here S where the field split. Early analyses using Keck in Hawaii and the VLT in Chile compiled hundreds of absorbers. The combined map didn't show a uniform drift, it hinted at a dipole, a directional pattern where alpha looked a touch higher in one hemisphere of the sky and a touch lower in the opposite. The amplitude, parts per million. The significance, intriguing, not decisive. The stakes, immense. A directional variation would mean the universe has a preferred axis baked into the constants themselves. But systematics lurk in every pixel. HL spectrographs can warp wavelengths across the detector. If your calibration lamp lines don't trace the same optical path as the quasar's light, tiny distortions masquerade as physics. Isotopes complicate things too. Absorption lines aren't single notes, they're chords from different isotopes. If ancient gas clouds had different isotope ratios than local lab samples, you could mistake chemistry for drifting alpha. Teams went back to basics. Laser comb calibrations to straighten the wavelength scale, cross-checks between instruments, explicit modeling of isotopic shifts for magnesium, silicon, iron. Conflicts sharpened. Some groups, using ultra-stable laser comb, calibrated spectra, reported null results, no significant variation in alpha when they restricted to the cleanest systems. Others, reanalyzing larger catalogs with updated calibrations, saw the dipole pattern persist, nudging toward 3 to 4 sigma across the full sky, but softening when you slice by redshift or instrument. One team spent months building a pristine sample, only to throw out a dozen absorbers after finding a single arc lamp exposure had saturated and skewed a wavelength solution. That decision moved their result from a 2 sigma hint to a shrug. They published the shrug anyway. Meanwhile, Webb's infrared eyes entered the story. Quasar absorbers at higher redshift shift into wavelengths Hubble couldn't reach. With Webb's stability and resolution, you can target transitions less vulnerable to blends and atmospheric contamination. Early Webb spectra added leverage at the extreme end, redshifts 5 and beyond, where the many-multiplet method is starved of clean lines. The first trickle of results did what you'd expect from a cautious universe. They tightened constraints and kept the door cracked. No sweeping drift, but enough room left for a subtle anisotropy if the systematics are truly tamed. Why would alpha vary at all? Theorists dusted off scalar field models where what we call constants are values of fields rolling slowly through space and time. In some versions, the same field that drives dark energy couples weakly to electromagnetism. If that field isn't perfectly uniform, alpha inherits a map. That would link the Hubble tension's dark energy suspicion to the quasar whisper. Tempting, but dangerous. Any coupling strong enough to move alpha must also thread through laboratory tests, atomic clocks, equivalence principle experiments, the oclo-natural nuclear reactor's ancient isotope ratios. Those are tight fences. Most viable models have to tiptoe. The consequences, if real, aren't academic. Shift alpha by a few parts per million and nuclear resonances budge. Decay rates we use as clocks tick at slightly different speeds. In stars, opacities change, altering how they transport heat. Molecular energies shuffle, changing how clouds cool and collapse into stars and planets. Chemistry's periodic table wouldn't rewrite, but the margins would smear. Life's comfortable window depends on molecular coincidences encoded by alpha. The whisper touches biology by way of astrophysics. Back in the data trenches, the human moments keep the guardrails up. A graduate student, 3 years into a thesis, realizes a telluric correction, Earth's atmospheric absorption, was misapplied in a subset of VLT spectra. The fix erases a tempting outlier. A competing team, midnight in a Slack channel, shares raw calibration frames with rivals because the only way to kill a distortion is to replicate it. A principal investigator tells their group, if we find a variation we don't believe, we publish the non-detection and sleep well. Meanwhile, clocks on Earth quietly listen. Optical lattice clocks comparing frequency ratios, ytterbium against strontium, aluminum against mercury, set world-leading bounds on present-day drift in alpha. Year over year, they report changes smaller than parts in 1018. Those are direct, local tests, and so far they point to stability. If the quasar dipole is real, maybe it's spatial more than temporal, or maybe the coupling is environmental, stronger in pristine intergalactic gas than in our dense, screened laboratory. That's a specific prediction some scalar field models make. Screening hides variations where matter is thick. This was the moment everything changed for alpha. The field matured from did we see something to can we rule out our own favorite error? The answer so far is humility. The best we can say is that alpha doesn't scream, it whispers. And the whisper is directional enough, faint enough, and consequential enough to keep telescopes pointed at quasars and labs locking lasers to atoms. If light's coupling even wobbles, gravity's grip won't be far behind. G, the most annoying constant in physics. If alpha whispers, G mutters and contradicts itself. Isaac Newton's gravitational constant looks simple on paper, one number that sets how strongly masses pull. In the lab, it's a gremlin. Tiny shifts in G would tilt planets' orbits, reshape stars, and ripple through everything that falls. That's the stake. Gravity is the stage on which every other law performs, and the stagehands can't agree how heavy the scenery is. The classic way to weigh G is a torsion balance. Two small masses on a bar suspended by a thin fiber, twisting ever so slightly toward larger masses nearby. You angle mirrors, bounce laser light, and red microradian twists like a seismograph for gravity. The signal is barely there, living in the space between air currents and the heartbeat of the building. Modern experiments bury these setups in basements, float tables on pneumatic legs, and chase thermal gradients with obsessive insulation. Still, the numbers disagree beyond their quoted errors. Meanwhile, a new generation tried a different trick: atom interferometers. Launch cold atoms upward in a fountain, split their matter waves, let gravity tug the paths out of phase and recombine. The interference fringes shift by an amount set by G when you move source masses around. It's gravity measured with quantum waves instead of twisting bars. Different systematic demons, same headache. When you line up results from torsion balances, atom interferometers, and pendulum variants, you see scatter that doesn't compress neatly into a single mean. The G paradox isn't that we don't know G. It's that our most careful methods disagree more than they say they should. Physicists built error budgets like crime scene boards. Thermal creep in fibers, microscopic changes in twist with temperature can mimic or mask signal. Seismic noise from distant traffic couples to the floor and then the fiber. Magnetic impurities in masses let minute fields tug where only gravity should. Even how you model the test masses, are they perfectly uniform, feeds uncertainty. In atom interferometers, wavefront aberrations, vibrations, and gravity gradients from nearby walls show up in the fringes. Labs tried blind analyses, swapping mass configurations without telling the analysts to see if expectations were biasing the fit. The spread narrowed. It didn't die. What would it mean if the spread were real? Planetary dynamics are a tight leash. You can't just crank G by 1% without Mercury telling on you. But the lab scatter is at the tens of parts per million level. Tiny, yet not nothing. At that scale, G shifts could tweak Earth's internal heat budget by changing how pressure and density trade off in the core models we use. In star formation, the threshold where gas clouds collapse versus stall depends on gravity's strength against thermal pressure. Move G and you move the line. In a universe that already struggles to form the smallest galaxies at the right times, that line matters. While basement labs wrestled with fibers and fountains, astronomers stared into a different gravity riddle. In spiral galaxies, stars far from the center orbit too fast if you only count visible matter. Lensing maps curve light more than starlight mass can explain. We call the extra pull dark matter, and the big picture model handles a lot. But the way gravity behaves on scales from labs to galaxies to the whole cosmos feels like a stack of rules glued together. Newton here, relativity there, dark matter on top, dark energy stretched across. If G were hiding a subtle environmental dependence, different effective strengths in different regimes, we'd be seeing only shadows of the deeper rule. There's a human moment here too. A team in Europe spends 18 months rebuilding a vacuum chamber around their torsion balance to chase a whisper of thermal drift. They switch to fused silica fibers to kill magnetic sensitivity. The new data lands a hair lower, tightening their uncertainty bars, widening the gap with a rival lab. They publish anyway, with a title that underscores the conflict rather than smudging it into a consensus. Across the ocean, an atom interferometry group runs nights with the building elevators locked to cut vibration, logging notes like pilots. One morning, their phase jumps by a fraction of a fringe when a delivery truck idles outside. They move the truck. The phase calms. The lesson sticks. Gravity is patient. Experiments must be more patient. The philosophical itch is hard to ignore. We treat G as a universal constant because it behaves that way in the equations that win. But the equations are effective, summaries of deeper behavior in certain limits. In some scalar tensor theories, the gravitational constant is really a field whose value can vary in time or respond to local matter density. Screening mechanisms hide variations in dense environments and reveal them in the thin intergalactic medium. If that's the game, then Lab G and Cosmic G are cousins, not clones. Most tests say any drift is tiny, but tiny is all it takes to stitch together anomalies that refuse to match. Here, where this links back to the broader glitch. If alpha might be nudged by a dark field, and G might be effective rather than absolute, then the constants aren't platonic numbers. They're settings the universe dials under conditions we don't fully map. The lab fights over G aren't a sideshow. They're a stress test for the idea that constant means constant. Out in the dark, on scales too big for wires and lasers, gravity keeps acting like it's missing a rulebook we keep trying to rewrite. The dark sector's two-headed monster. Out in the dark, gravity acts like it's missing a rulebook. 95% of the cosmic budget is booked under two line items we can't see: dark matter and dark energy. They're placeholders that behave like facts. One clumps, one pushes. Together, they keep the visible universe in its lane, most of the time. The first head showed itself in the 1970s when astronomers mapped how fast stars orbit in spiral galaxies. Far from the center, where starlight thins, speed should drop. They didn't. The curve stayed flat. Later, gravitational lensing traced the same story in the way galaxy clusters bent background light. There was mass the stars couldn't account for, sitting like invisible scaffolding. You could tweak Newton's law, or you could add missing mass. The field split, then the evidence piled up. The cosmic web of structure, the pattern of the CMB's acoustic peaks, all of it looked cleaner if you let cold, slow-moving dark matter seed galaxies and clusters. The second head arrived like a plot twist. In the late 1990s, two teams measuring distant Type Ia supernovae expected to see the universe's expansion decelerating under gravity. Instead, the light said expansion was speeding up. The simplest fix was a cosmological constant, energy inherent to space itself. Call it dark energy. It doesn't clump. It dilutes differently than matter. And once you add it to the equations, the supernovae, the CMB, and baryon acoustic oscillations line up into a model that fits nearly everything with 6 parameters. That model, lambda CDM, became the default rulebook. But default isn't destiny. The Hubble tension pressed its thumb on the scale, and the first suspect many reached for was dark energy's mood. If the lambda isn't a true constant, if it changes with time, then the sound horizon inferred from the early universe could shrink, lifting the CMB's inferred Hubble constant toward the latter's number. Early dark energy models tried exactly that, a field that turns on briefly around recombination, contributing a few % of the energy budget, then fades. The payoff is surgical. You touch the era that sets the acoustic ruler without wrecking late-time successes. That surgery leaves scars you can look for. Early dark energy changes the exact spacing and heights of the CMB's acoustic peaks. It tweaks how structure grows, shifting the amplitude we summarize as S8. If you're watching weak lensing surveys weigh the clumpiness of matter, you should see the ripple. Some analyses did hint at a slightly lower S8 than Planck prefers, which made early dark energy tempting. But push too hard and you break something else. The models that erase the Hubble tension cleanly often pull S8 the wrong way or demand extra relativistic species that other measurements constrain. The field lives in this narrow canyon where a small pulse might help without toppling the bridge. Meanwhile, dark matter itself refuses to sit still. On galactic scales, the way rotation curves rise and the tight relation between observed acceleration and baryonic mass, the radial acceleration relation, look almost too clean, as if gravity is being gently modified. In big clusters and in the CMB, invisible mass acts like particles. At small scales, pure cold dark matter predicts dense central cusps and too many satellites compared to some observations. Baryonic feedback, supernovae and black hole winds, can reshape halos, but the bookkeeping is messy. Theories sprouted in the cracks: warm dark matter to smear out small structures, self-interacting dark matter to puff up cores, superfluid phases that mimic modified gravity inside galaxies while behaving like particles in clusters. Here's the connective tissue to our glitch. If the constants we trust are really parameters of fields, then the dark sector can carry those fields. A scalar that drives cosmic acceleration could couple tiny amounts to electromagnetism, or to the strengths of forces in ways that are screened in dense environments. That would make alpha look directionally different in the thin intergalactic medium while keeping labs quiet. It would also make the effective pull of gravity shift with environment, reconciling galaxy regularities with cluster-scale demands. Not a conspiracy, just a network of settings that move together. The data keeps pressing. Baryon acoustic oscillations draw a precise ruler across cosmic time. Supernovae measure how bright that ruler looks at different epochs. Weak lensing maps how structure clumps and shears light. Strong lens time delays solve geometry with clocks. Each probe has its own systematics, its own quiet traps. Together, they squeeze the dark sector into a corner. The corner still has room. There's a human beat here too. A collaboration splits into two analysis teams with firewalls, each allowed to choose different cuts and calibrations. Then they meet to compare blind results. The numbers land close but not identical. The debate over which systematics to trust runs long. A junior researcher, staring at a lensing shear catalog at midnight, notices a subtle correlation with telescope-focused drift that shouldn't be there. They build a correction, and the S8 value slides by a hair. Enough to keep hope alive, not enough to claim victory. So where does the monster lead us? Maybe dark matter is a simple particle and dark energy a simple constant, and the cracks are our instrument fingerprints. Or maybe both heads are masks for deeper fields whose ripples show up as tensions, drifts, and anisotropies when our measurements get sharp enough. The stakes are simple to say and hard to solve. If the dark sector evolves, the constants we use to describe it might be evolving too. To test that, we need a yardstick deeper than galaxies and a snapshot older than starlight. Ancient light is waiting. Ancient light, modern doubt reading the CMB. To test dark stories, you go back to where the universe first cleared its throat. The cosmic microwave background is that moment, ancient light set free when electrons and protons finally married into neutral atoms and the fog thinned. It's our baby photo. But a baby photo can lie if you angle the light wrong, or if the camera adds its own signature. That's the risk. Read it right and you get a ruler for everything that follows. Read it wrong and every conclusion leans. The CMB isn't a smooth wash. It's a patterned sea of hot and cold freckles. Those spots trace sound waves, compressions, and rarefactions, ringing through the primordial plasma. Plot their sizes and you get acoustic peaks, a set of harmonics like notes on a drum. Each peak's position and height tell you about the universe's contents then. How many baryons, how much dark matter, how much radiation, and how tightly gravity and pressure were wrestling. From that, you can infer the sound horizon, the distance a wave could travel before light decoupled from matter. That's the ruler the CMB hands you. Here's the subtlety. The CMB gives you a snapshot with parameters woven together. Increase baryons and you deepen odd peaks relative to even ones. Add relativistic species and you shift the phases. Change spatial curvature and you bend the paths light took. The Hubble Constant isn't directly measured on that screen. It's inferred by fitting a model where all those knobs turn together. Get the model right, the inference is powerful. Get a prior wrong, and the fit compensates in ways that look like certainty. but are really assumptions. Planck's satellite gave us the sharpest map yet. Its peaks line up so cleanly that the 6-parameter model feels inevitable. But look closer, and there's a handful of features that nag. Anomalies at large angular scales, where cosmic variance dominates and statistics are thin. There's a cold spot in the southern hemisphere that's larger and deeper than simple Gaussian expectations prefer. There's an eerie alignment between the quadrupole and octopole, low-order multipoles pointing along similar axes, that some nickname the axis of evil, half jokingly, half nervously. There's a hemispheric power asymmetry. One half of the sky looks a little more lumpy than the other. Are these physics or a roll of the cosmic dice? The debate won't die because the significance floats in the 2-3 sigma fog, and because the features rhyme with other whispers, dipoles, alignments, that hint at preferred directions. Some argue local structure could imprint part of the cold spot through the integrated Sachs-Wolf effect, as light climbs out of evolving potential wells and loses or gains energy. Others show that when you scrub the data with different masks, foreground models, or component separation algorithms, the anomalies wobble. They don't vanish. They don't harden into stone. They sit in the uncanny valley between fluke and clue. Meanwhile, parameter degeneracies do real work behind the scenes. Say you try to rescue the Hubble tension by adding early dark energy. You're effectively shrinking the sound horizon at recombination so that a fixed observed angle corresponds to a shorter physical distance, which means a larger late-time Hubble rate when you stitch to supernovae and bow. But that same change nudges lensing of the CMB, how clumpy matter bends those ancient photons on their way to us, and it shifts the inferred amplitude of structure. Planck's internal consistency checks push back. The fits trade off H against S8, against the optical depth to reionization, against the number of effective neutrino species. You can slide along ridges in parameter space, but the ridges are narrow. Here's a human moment. A graduate student, eyes dry from too many nights with a sky map, notices the low multipoles line up with the ecliptic plane more than they should. It looks like a solar system fingerprint stamped on the baby photo. They draft an email they know will be unpopular. If it's real, it means an unmodeled artifact survived the pipeline. Their advisor replies at 3 a.m. Run the null tests again, rotate the masks, invert the component separation. 3 weeks later, they present a quieter conclusion. The alignment weakens under stricter foreground cuts but doesn't disappear. The room exhales. Not a clean error, not a clean signal. The student learns the rhythm of doubt. What nobody knew during Planck's heyday was how much the late-time probes would leverage the same ruler. Baryon acoustic oscillations, fossil ripples in galaxy clustering, depend on that sound horizon too. If your early universe fit underestimates uncertainties in the ruler, everything Bao touches inherits the bias. That's why the choice of priors matters. Analysts began to publish prior-free or agnostic reconstructions, letting the data dictate combinations of parameters without assuming a specific dark energy model. The result? The low H inference remains stubborn, but the error bars breathe a little wider when you loosen the leash. Meanwhile, polarization maps add their own constraints. The E-mode pattern at degree scales pins the reionization history, when the first stars lit up and started reionizing hydrogen, and that cascades back into the optical depth parameter, which trades against the amplitude of primordial fluctuations. Small changes there ripple into S8 and lensing amplitudes. The data sets braid together, and small mismatches in one strand tighten the whole plate. Through all of this, the CMB's status is double-edged. It's our best early anchor and our biggest model mirror. Its beauty is how much it tells you with so little input. Its danger is how easy it is to mistake model confidence for cosmic truth. The field's response has been healthy. Split analyses, blind pipelines, independent instruments like ACT and SPT to cross-check Planck, and forecasts for the next generation, Simon's Observatory and CMB S4, to push polarization noise down and lensing maps up. If early dark energy left fingerprints, finer maps might find them. If anomalies are flukes, bigger samples will wash them out. So where does ancient light leave us? With a ruler that's precise, a model that's elegant, and a handful of patterns that refuse to be either fully dismissed or fully embraced. The CMB doesn't settle the argument, it sharpens it. While the sky whispers in microwave, clocks on Earth start arguing in optical, and the question shifts from what's the number to what's the rulebook that makes all the numbers agree. Atomic time versus cosmic time, the clock wars. While the sky whispers, the argument moves to tables of glass and vacuum. If constants drift, the most honest snitches aren't telescopes, they're clocks. Not the ones on your phone. Optical lattice clocks that trap thousands of atoms in laser-made egg cartons and count the wiggle of light with a precision that makes nanosecond sound sloppy. If alpha or the electron-to-proton mass ratio budges, frequency ratios between different atomic transitions will tilt. Compare enough clocks long enough, and time itself testifies. Here's the stakes in human terms. GPS corrections, financial timestamping, geodesy that maps Earth's gravity by watching how clocks tick faster on hilltops than in valleys. Our world already leans on precision time. A real drift means software patches at planet scale. It also means the laws we teach are provisional in the second decimal place of reality. Inside a clock lab, the air smells faintly of electronics and anxiety. Strontium atoms, cooled to microkelvin, line up in a lattice made by interfering lasers. Ytterbium plays the same game down the hall. Aluminum sits in an ion trap, a single glowing dot, interrogated by a clock laser tuned so tightly it's like playing a single note for days without wavering. Each species counts a different transition, different sensitivity to alpha, to the strong force through nuclear structure, to the electron mass. That's the trick. You don't ask one clock if time drifts. You ask whether one clock drifts relative to another. Ratios cancel the Earth's motion, the lab's temperature, most of the dirt, and leave you staring at the constants. Year over year, teams run comparisons. Frequency combs optical rulers with evenly spaced teeth, link colors of light across the spectrum, letting you compare strontium's red to aluminum's ultraviolet without getting lost. Results have escalated to the absurd. Agreement at parts in 1018, a sensitivity where raising a clock by a centimeter makes it tick measurably faster. At that scale, the planet's own heartbeat is in the data. Clocks argue when someone walks past a table. So what's the score? Reported bounds say no detected temporal drift, at least not here and now. Translate that. If alpha or the mass ratio is sliding, it's doing it slower than roughly a part in 1018 per year in the lab's environment. That rules out whole swaths of scalar field models that would shake electromagnetism too hard. It doesn't kill the spatial dipole idea from quasars, because those could be environmental, stronger in thin intergalactic gas than in dense labs, or purely directional, not evolving in time where we sit. But the fence got taller. Environmental demons are the daily grind. Temperature gradients nudge cavity lengths by a hair, shifting laser frequencies. Blackbody radiation from the chamber walls bathes atoms and shifts levels by tiny amounts. You measure the wall temperature to a fraction of a degree and still argue about emissivity. Magnetic fields leak in from transformers floors away and line split transitions. Vibration couples to mirror mounts. An elevator ride 2 floors up leaves a ghost in your data. You learn to schedule, runs when the building sleeps. Here's a micro story. A team at 2 a.m. is comparing ytterbium to strontium for the 100th time. A graduate student notices a weekly drift that shouldn't exist, always peaking on Monday mornings. It takes 3 weeks to trace it to an HVAC cycle that warms a duct behind a rack by half a degree. They wrap the duct in insulation and the drift vanishes. The student scribbles a note. Time hates Mondays too. The ratio, freed of its phantom, tightens the bound on alpha's drift again. Meanwhile, a different kind of clock steps outside. Space-based missions are on the drawing board. Fly an optical clock on a quiet platform above the atmosphere, link it to ground clocks with stabilized lasers, and watch how ratios change as you move through gravitational potentials and magnetic environments. If screening hides variations in dense regions, a clock in space might see a slightly different effective alpha than the one in a basement. It's a clean test. Same atoms, new context. Network thinking is taking over. Instead of one perfect instrument, you build a web: strontium in Boulder, ytterbium in Tokyo, aluminum in Paris, mercury somewhere else, linked by undersea fiber and free space optical links. The network listens for correlated blips, a global twitch in a ratio that can't be blamed on a single lab's glitch. If a dark field rolls through like cosmic weather, clocks become detectors, ears for a hum we haven't named yet. There's another twist. Gravitational waves and standard sirens can arbitrate H, but clocks can weigh gravity locally in a new way. Relativistic geodesy pulls topography out of tick rates. Clocks map equipotential surfaces. If G were effective, subtly environment-dependent, long-term clock networks might see seasonal breathing in ticks tied to Earth's mass distribution shifts, beyond the known tides and loading. No claims yet. Just a frontier where metrology becomes geophysics, becomes cosmology. Skeptics keep the room honest. They point to the Oklo natural reactor 2 billion years ago, whose isotope ratios fence alpha's ancient value, and to equivalence principle tests that punish any coupling between new fields and matter. True, but those are snapshots in different regimes. Clocks give you the movie, one frame per day, with the power to catch a surprise. So where do the clock wars leave us? With a sobering message: if constants move, they're shy. With a thrilling one: we finally have tools sharp enough to hear them whisper in real time. And with a bet: one clock in space linked to a dozen on Earth could settle whether the drift is here, elsewhere, or nowhere. While proposals turn into hardware, the ratios keep scrolling, the noise floors keep dropping, and time keeps telling us whether the rulebook is ink or pencil. Early dark energy and the patch notes theory. Remember the stakes from the latter fight. If the early snapshot is pulling H low, maybe the snapshot is missing a brief chapter. That's the itch behind early dark energy. The idea sounds simple and audacious. Around the time the CMB formed, a small extra energy component briefly turned on, just a few percent of the total, and then turned off. It didn't dominate the universe, it nudged it. That nudge shrank the sound horizon, so the same angular peaks on the CMB correspond to a shorter physical ruler. Stitch that ruler to late time distances, and the inferred Hubble rate ticks higher. Suddenly, 67 inches towards 70 plus without wrecking the rest. How would the cosmos do that? Theorists reached for scalar fields, smooth, slowly rolling quantities that can carry energy density without clumping like matter. In these models, the field is frozen by cosmic drag early on, contributing almost nothing. Near recombination, friction eases, the field wakes up, contributes that crucial few percent, then quickly dilutes or gets trapped again so it stays quiet later. Mathematically, you write a potential that lets the field loiter on a plateau, then slide, then stall. Physically, you get a pulse, on-off with fingerprints in the acoustic peaks and lensing. Here's the catch. The CMB is a jealous bookkeeper. A pulse at recombination changes more than just the ruler. It tweaks the ratio of peak heights, shifts phases, and alters how much those ancient photons get deflected by the clumpiness of matter along the way. Planck's maps aren't friendly to sloppy pulses. The viable models thread a narrow path, enough early energy to lift H, not so much that you overlens or me-shape the peaks. Papers became a dance of parameter scans. How much early energy when it turns on redshift Z 300-500? How fast it shuts off, whether it talks to neutrinos or remains aloof. While that dance played out, another tension slid onto the stage, the S8 problem. Weak lensing surveys, DES, Chi-DS, HSC, kept hinting that the present-day universe is a touch less clumpy than Planck's base model wants. If early dark energy simply raises H by shrinking the ruler, it can accidentally goose the growth history, pushing S8 the wrong way. That's why the patch can't be just a slider, it needs nuance. Some variants couple the field to dark matter, letting it drain a little momentum from growth. Others add a breath of extra relativistic species, dark radiation, to adjust phases and lensing together. Each tweak buys room in one corner and spends it in another. Think of it like software patch notes for reality. Version 380K or added brief early dark energy pulse, fixed sound horizon bug, known issues excess lensing power S8 drift. Then you push a point release, version 380K or 1, reduced coupling to matter, adjusted neutrino-like degrees of freedom by 0.2, mitigated lensing overshoot. The metaphor fits because the model lives or dies on specific changelogs, testable fingerprints, not hand-waving. What would those fingerprints look like? Slight shifts in the high-L damping tail of the CMB temperature and polarization spectra. A lensing amplitude preference that moves closer to ACT and SPT measurements. Bow distances that still line up once you adopt the shortened ruler. And a growth history that threads the S8 needle. It also predicts small changes in the inferred epoch of matter radiation equality and in the phase of the acoustic peaks, which next-gen polarization data can stress test. In principle, a standard siren, gravitational waves from a binary with a clean redshift, could triangulate H without the sound horizon entirely, offering an outside judge. What nobody anticipated at first was how sensitive the whole story is to priors. If you assume the simplest dark energy at late times, a pure cosmological constant, you can find the allowed wiggle room early on. If you let late-time dark energy breathe a little, the fit can relax in early epochs too. Analysts reacted by building agnostic reconstructions. Let the data piece together the expansion history in bins, with minimal assumptions on the shape. Those reconstructions don't crown early dark energy, but they keep a lane open for a brief pulse. Meanwhile, structured data join the jury. Cluster counts, redshift space distortions, and lensing all respond to how fast the universe grows lumps. Teams now run global fits that mix CMB, bow, supernovae, lensing shear, and sometimes the first standard sirens. Results land in a frustrating middle. Early dark energy eases the H tension to a draw for some combinations, but the S8 relief is partial, and some internal Planck checks raise an eyebrow. It's not a slam dunk. It's a plausible edit. Here's a human beat. A small theory group spends a semester building a model where the scalar field talks to neutrinos that briefly become mildly interacting near recombination. They name the parameter yawn in the code because it's supposed to be barely there. The fit improves H and softens lensing. They're excited. Then they realize their neutrino tweak messes with Big Bang nucleosynthesis enough to spoil deuterium abundances. They post the preprint anyway, with a sober appendix on the failure mode, because negative results steer the search as much as wins. So what would it take to falsify the patch notes theory? Data that nails the CMB polarization peaks, and lensing to the point where any early pulse leaves a mismatch too big to ignore. Bow at higher redshift from Dacey and Euclid that lock the ruler without Planck's priors. A stack of standard sirens that triangulate H to 2% and pick a side. Cross correlations between lensing maps and CMB lensing that close the S8 loophole. Those aren't dreams, they're scheduled observations. If early dark energy is right, we'll catch the universe mid-patch, a subtle time-bound shift in the rulebook that explains why our two clocks read different times. If it isn't, the exercise still pays off, because it forces us to test which assumptions are load-bearing and which are decorative. And it sets the stage for a reminder. Not every glitch worth studying is cosmological. Some are local, small, and stubborn, the kind that show up in our own backyard and refuse to leave quietly. Solar system oddities, the Flyby and Pioneer puzzles. If the universe patches itself, you'd expect the bugs to show up everywhere, even at home. Spacecraft don't care about our theories, they follow forces. That's why a handful of tiny, stubborn anomalies in our own backyard earned attention far beyond their size. Millimeters per second, nanometers per second squared. Numbers so small you'd miss them in a breath, unless your instrument is a spacecraft and your test range is the solar system. Start with Pioneer. In the 1970s, Pioneer 10 and 11 slipped past the giant planets and coasted into the dark, tracked by the Deep Space Network's patient ears. As the data piled up, navigators noticed something off. A steady, sunward acceleration of about 8 times 10 to the minus 10 meters per second squared. Not wild, not loud, just a gentle extra tug that made the crafts lag behind their predicted positions by billions of meters over decades. Teams interrogated everything. Was gravity wrong? Was interplanetary dust dragging? Were clocks or ephemerides off? What nobody knew at first was that heat has a direction. The radioisotope generators on Pioneer ran hot, and heat radiates. If the thermal photons preferentially left the spacecraft in one direction, off the back, say, the recoil would act like a tiny thruster. Modeling that meant engineering archaeology, digging up decades-old telemetry, reconstructing the craft's geometry, and solving a radiation puzzle with materials that aged in deep space. The answer took years, but it landed clean. Thermal recoil explained the anomaly within uncertainties, a mystery that felt like new physics turned out to be old heat. That resolution mattered. It reminded everyone that elegant deviations die the same way messy ones do, with painstaking accounting. It also set a tone. Don't reach for modified gravity until you've emptied the drawer labeled mundane. And yet, just as Pioneer faded, another whisper popped up closer to home. During Earth flybys, spacecraft sometimes steal a little speed from our planet's motion, a gravity assist maneuver that's pure Newton and Einstein. Navigators expect energy to balance in the Earth-fixed frame. But a few missions came away with tiny, unbudgeted velocity jumps, millimeters per second, after skimming the atmosphere and slingshotting away. Galileo saw it. NEAR did. Rosetta and Messenger had hints. Others didn't. The pattern was aggravating. Not universal, not random, and not obviously tied to altitude, inclination, or perigee time. The error bars were honest. The effect was small, and it was real enough to publish. The first suspects were always tracking and geometry. Doppler fits can be biased by where you switch from one ground station to another. Earth's oblateness, atmospheric drag, solar radiation pressure, and thermal recoil all nibble at a trajectory. General relativity adds frame dragging and gravitational time dilation, but those are accounted for. One proposed formula tied the anomaly to declinations of the incoming and outgoing asymptotes, hinting at Earth's rotation and the latitude of the tracking network as a culprit. It fit some cases. It missed others. That's the mark of an almost right theory. It charms for a week, and then the next data point shrugs. Engineers, in the best sense of the word, went to war with the details. They reprocessed tracking arcs with higher fidelity atmospheres. They swapped antenna calibrations. They fed spacecraft thermal models into trajectory fits, looking for Pioneeresque recoil. They tightened Earth gravity field models using GRACE and GOCE data, reducing the wiggle room in geopotential harmonics. The anomalies shrank. They didn't vanish. Each mission became a case study, a courtroom drama where the defendant is a missing millimeter. Why does this matter in a film about cosmic constants? Because if gravity or inertia has a small, environment-dependent tweak, if the rulebook has a footnote in rotating frames, or if dark sector fields couple to motion in subtle ways, then the first place you see it is in the cleanest, simplest experiments you can run, tracking a spacecraft. Modified inertia ideas orbiting MOND tried to grab the flybys. So did models with anisotropic light speed in rotating frames, or tiny violations of Lorentz invariance that only show in particular geometries. None survived full scrutiny, but the temptation taught a discipline. Use anomalies as sharpening stones, not as soapboxes. Here's a micro-story from that world. An engineer at a deep space navigation team quietly bets a career on a millimeter per second. Their job is to sign off on a trajectory correction burn that costs fuel you don't get back. The residuals say there's an extra tick in speed post-flyby. The safe play is to call it noise and spend the propellant. Instead, they push for one more round of thermal modeling, one more ground station handover audit. The burn is delayed by 12 hours. The new fit absorbs the tick, and the mission saves fuel it will need 2 years later. Nobody outside the room hears about it. Inside, trust goes up a notch. Meanwhile, the Pioneer lesson keeps paying interest. When New Horizons flew past Pluto, its team carried a full thermal recoil model from day one, treating heat as thrust. Its navigation residuals stayed boring, and boring is a victory. Cassini's years at Saturn refined gravity fields and dragged atmospheric models into the spotlight. Juno's Earth flyby was watched like a hawk. Its anomaly was negligible within improved models. The more we looked, the less room remained for magic. And yet, a few data points still don't sit right. Some of the old flyby cases resist perfect reconciliation even after reanalysis. The honest stance is twofold. First, we've learned that most glitches shrink under brighter light. Second, the ones that don't deserve that light, not stories of new physics by press release. A solar system anomaly is a gatekeeper. If a theory can't thread a millimeter per second under the best models of Earth's gravity, atmosphere, and instrument quirks, it doesn't deserve the galaxies. So we keep tracking, we keep modeling, and we learn a habit the cosmos requires: patience with small numbers. Zoom out, galaxies still don't care about our neat equations. The local puzzles are training. The real fight over gravity's rulebook is written in starlight and lensing arcs, not in the third decimal place of a Doppler fit. MOND versus Lambda CDM, a tale of two rulebooks. While spacecraft tested patience, galaxies demanded a verdict. Two rulebooks sat on the table. One said, keep gravity, add invisible mass. The other said, keep the mass, tweak gravity when accelerations get tiny. Lambda CDM versus MOND, particles versus a new regime. Both could sketch a spiral galaxy swirl. Both claim the high ground for different reasons. Start with the cleanest arena, disk galaxies. Plot how fast stars orbit versus radius, and you get curves that stay flat instead of dropping. In the particle story, halos of cold dark matter surround galaxies, their gravity making up the difference. In the modified story, MOND, short for modified Newtonian dynamics, something else happens when acceleration falls below a universal scale. Below that threshold, the effective pull grows stronger than Newton's law predicts, and rotation curves flatten without adding hidden mass. Here's the shocker. If you hand MOND the visible baryons, it nails many rotation curves with almost no extra freedom. Even more, it predicts a tight relation, the radial acceleration relation, between the observed acceleration and the one expected from the baryons alone. Data fell on that line like iron filings on a magnet. But galaxies aren't the whole universe. Take MOND to galaxy clusters and the story phrase. In clusters, even with MOND's boost, there isn't enough gravity from visible stuff to explain the lensing and dynamics. You still need unseen mass. In the bullet cluster, two clusters colliding leave gas, the baryon heavyweight, lagging behind while the lensing mass sails ahead with the galaxies. That looks like particles, not just modified laws. Lambda CDM points and says, this is your smoking gun. Lambda CDM's case is broad. It explains the CMB's peak pattern, the growth of the cosmic web, and the abundance of light elements through a simple 6-parameter model with cold dark matter and a cosmological constant. Run simulations with those ingredients and you get filaments and halos where galaxies live, large-scale structures that match surveys, and lensing statistics that pass test after test. Where it stumbles is small scales. Pure cold dark matter predicts dense central cusps in halos and too many small satellites compared to some observations. Baryonic feedback, supernovae blasting gas, black holes stirring cores, can flatten cusps and thin satellites, but it asks you to believe violent astrophysics can unmake what gravity made. Maybe it can. Maybe we're tuning subgrid recipes until the outputs please us. MOND's believers don't deny clusters or the CMB. They build extensions. TVS tensor vector scalar gravity wraps MOND-like behavior into a relativistic theory that can bend light properly and act like general relativity in the right limits. It reproduces some lensing and CMB features, but pays with complexity and tight constraints from cosmic microwave background fits and gravitational wave speed. Other ideas try emergent roots, gravity as an elastic response of spacetime's microscopic degrees of freedom, where an extra entropic push shows up at low accelerations. These attempts aim to keep MOND's galaxy magic while dodging its high-scale headaches. The price is theorist sweat and new parameters that can smell like the particles MOND tried to avoid. Meanwhile, particle dark matter diversified. Warm dark matter with a small free-streaming length softens small-scale structures. Self-interacting dark matter lets particles scatter, lowering central densities in halos. Superfluid dark matter is a hybrid. In galaxies, dark matter condenses into a superfluid whose phonons mediate a MOND-like force. In clusters, where conditions break superfluidity, it behaves like standard particles. It's an audacious bridge, promising MOND's precision in disks and lambda CDM's reach in the CMB. And it predicts distinctive core shapes and interference patterns you can hunt. Here, where the two rulebooks reveal a deeper lesson. Laws might be shortcuts, effective summaries of underlying complexity that look simple only in certain regimes. In that view, MOND is a brilliant asymptotic formula, a low acceleration rule that falls out of deeper microphysics we haven't written down yet. Lambda CDM is a broad-stroke scaffold, a statistical story about an invisible sector that gets the early universe and large structures right, and hands the messy baryons to astrophysics. Neither is the full code. Each is a page that works where it was designed to work. Stakes land in human hands again. A small team spends nights fitting rotation curves with a single stellar mass-to-light ratio, and MOND's the fits hug the data. The residuals look like instrument noise. Across the hall, a simulation group runs a cosmological box with feedback turned to 11. Their mock galaxies grow cores and align with the same radial acceleration relation MOND touts, not because gravity changed, but because galaxies self-regulate under feedback. The hallway debates are civil, pointed, unresolved. What tilts the scales? Lensing maps that see mass without caring how stars shine. Satellite galaxy planes that may or may not be statistical flukes. Strong lenses where time delays pin down potentials independently. Ultra-diffuse galaxies that appear to have almost no dark matter, or almost only dark matter, challenging both camps to explain the extremes. And soon, precise proper motions from the Gaia era extended, letting us weigh halos with six-dimensional phase space data rather than squinting at line-of-sight velocities. The fight exposes more than preference. It exposes our habit of mistaking a successful fit for a final truth. If laws are shortcuts, the right question is which rulebook wins. It's what deeper mechanism makes both rulebooks look right where they do. Maybe the dark is particles that can condense into phases that mimic new forces. Maybe gravity is emergent and matter's distribution tunes the emergent response. Maybe both. The path forward isn't loyalty, it's prediction. Everything was about to change when new instruments arrived with the power to choose. If laws are shortcuts, the next decade will tell us who picked them and whether the shortcuts can bend. The Anthropic trap and the landscape. If laws are shortcuts, it's tempting to dodge the puzzle with a simple move. Maybe we live where the shortcuts happen to allow us. That's the Anthropic lane. It says, of all possible universes, you only ever wake up in one where stars burn long enough, chemistry hangs together, and brains can ask questions. If the constants drift through a landscape of options, Then of course we see values that look tuned. We're here because we can be. Here's the hook and the hazard. The fine structure constant sits in a narrow comfort zone. Nudge it upward and nuclear resonances shift. Carbon yields in stars can plummet. Nudge it downward and hydrogen chemistry changes. Stellar lifetimes wobble and the periodic table gets less friendly. The same with the cosmological constant. Make it much larger and galaxies don't condense before space rips them apart. Make it negative and the universe recollapses too soon. Those boundaries sketch a target. We're standing on it. That can feel like an answer. But treat that feeling like wet paint. The anthropic trick can explain anything and predict nothing if you're not careful. We observe X because otherwise we wouldn't be here. Becomes a catch-all that stops curiosity. It can blind you right before the turn. Worse, it can smuggle your biases in and call them selection effects. The trap isn't in admitting observers select worlds. The trap is using that to excuse a lack of mechanism. The string landscape sharpened the temptation. In some versions of string theory, compactifying extra dimensions yields a vast menu of low-energy vacua with different constants, particles, and couplings. A cosmic multiverse, bubbles with different settings, could populate that menu. Eternal inflation scatters patches with different vacuum energies. Anthropic selection then picks out the few where galaxies form and life has time to emerge. It's clean on a whiteboard. It's messy in practice. What nobody agrees on is measure. If there are infinitely many bubbles, how do you count them? How do you define typical when every outcome occurs infinitely often? Different measures weight different patches differently and produce different predictions. That's not a prediction. That's a choose-your-own ending. And yet, one blunt anthropic argument did score a hit. The cosmological constant looks suspiciously close to the largest value that still allows structure. Weinberg called that shot before supernovae found acceleration. That matters. There's also a subtler lesson. Selection can work inside a single universe, not just across many. Even if the landscape exists, we only ever probe one path through it. Our data are conditioned by our environment. A galaxy type that can host us, a metallicity history that seeds planets, a position not too close to active cores that bathe space in radiation. Observer bias is real, and it's not a cheat. It tells you to correct your priors when your vantage point is special. We shouldn't be surprised. We're surprised by alignments near the ecliptic if our pipelines still whisper solar system fingerprints. We shouldn't mistake a trend in galaxy surveys for a universal rule if our sample selection quietly favors easy-to-observe systems. Here's a human moment. A young theorist pitches a talk titled Life Picks Lambda. The room splits before the first slide. Some nod, it's honest-to-face selection. Others bristle, it feels like surrender. Afterward, the questions circle one demand: where's the falsifiable part? The theorist concedes there isn't one yet. They add a line to the final slide. Anthropic reasoning is a lens, not a law. That's the balance. Use the lens to set expectations. Constants that look tuned might be tuned by survival. Use it to frame tests. If a parameter is anthropically selected, then pushing it off the edge should crash habitability in models of star formation, planet assembly, and biochemistry. But don't stop there. Ask for dynamics. Ask how fields settle, how inflation populates vacua, how tunneling proceeds, how reheating imprints relics. If there's a landscape, its geography should leave fossils. Domain walls we don't see, isocurvature we can bound, correlations between seemingly independent constants that betray a shared origin. Counterpoints pile up. Some physicists argue the landscape drains predictive power from string theory until it's unfalsifiable as a theory of our world. Others see it as statistical physics at cosmic scale. You don't predict a single atom's velocity, you predict distributions. The right move might be to demand coarse-grained predictions, likelihoods for classes of universes, correlations that must hold if anthropic filtering is doing the heavy lifting. There's also meaning. People don't only want parameters, they want purpose. The multiverse offers no comfort there. It swaps meaning for sampling. That can feel thin. But there's a different take. Purpose isn't something physics owes us. Pattern is. If the constants are drawn from a distribution set by deeper microphysics, then our job is to infer the distribution from one draw and whatever fossils we can find. Back to our glitch. The Hubble tension, alpha whispers, G's stubbornness, dark sector puzzles, Anthropic logic can sit in the background as a guardrail. It says, don't be shocked if reality lounges near boundaries, but the work is still to map the mechanism. The landscape, if real, is a context, not a conclusion. We still need a story that flows, fields, dynamics, emergence. So we hold two thoughts. Selection effects are real. They keep us honest about our vantage point. They're not a get-out-of-explanation-free card. The itch for meaning is human. The demand for mechanism is science. The next step won't come from declaring we're here, therefore. It'll come from models that predict which constants can drift, by how much, in which environments, and why. And if there's a landscape, we'll know we've escaped the trap when it predicts a feature we didn't ask for, and we find it. Emergence, holography, and codes without coders. If constants feel like settings, maybe the settings come from the way information arranges itself. That's the emergence bet. Laws aren't engraved. They're the habits of large systems. Water doesn't have equations. Molecules colliding find Navier-Stokes. Maybe spacetime does the same trick. If so, the numbers we call fundamental could flow with scale or state, quietly, rarely, but enough to leave fingerprints. Holography is the sharpest hint that gravity might be bookkeeping for information. Start with a black hole. Its entropy scales with the area of its horizon, not the volume inside. That's bizarre if you think in 3 dimensions. It's natural if the interior is encoded on a 2-dimensional boundary. Add SCFT took that hunch and made it a dictionary. A gravity theory living in a bulk spacetime is exactly equivalent to a quantum field theory without gravity on the boundary. 2 descriptions, 1 physics. Change couplings on the boundary, geometry in the bulk reshapes. The message lands. What looks like curved space can emerge from entanglement patterns. Here, S where variable constants sneak in. In the boundary theory, couplings run. They depend on energy scale through the renormalization group. Slide the microscope and the effective strength of interactions flows. Translate that to the bulk and you get geometries that shift with scale, horizons that puff or pinch, and effective couplings for forces that look different in different regions. It's not that alpha literally changes in the ultraviolet of QED. It's that effective descriptions always carry flow. If spacetime itself is an effective description, then the constants that live in it might inherit environment and scale dependence. Quantum error correction adds guts to the metaphor. To keep a bulk geometry robust, the boundary has to encode information redundantly, like a good code that can lose a few bits and still recover the message. Tensor network toy models, perfect tensors stitched into lattices, reproduce bulk-like distances and causal structure just from entanglement wiring. Lose too many boundary qubits and recovery fails. The interior phrase. That's a picture of geometry as code. Constants then look like code parameters. How dense the checks are, how deep the redundancy runs, how tolerant the code is to noise. If the universe changes phase, if the entanglement pattern reorganizes, those parameters shift. Phase transitions aren't only for water. Vacua, lowest energy states of fields, can undergo transitions as the universe cools or as conditions change. In condensed matter, order parameters jump or slide. Symmetries break, new excitations appear, and effective constants change across the boundary. Translate that to fields that set gauge couplings or to a gravitational sector that emerges from microstates. Constants become order parameters. Most of the time they're pinned. Occasionally, near critical points, they flow. In that regime, a tiny nudge, density, temperature, curvature, could glide a value by parts per million. That's the alpha whisper tuned to a physical knob. What failure looks like is as important as what success looks like. If geometry is held together by entanglement, then decoherence, information leaking to an environment, can peel off the glue. In toy models, scramble the boundary in the wrong pattern and bulk distances warp. Cut too many bonds and regions disconnect. In a real cosmos, wrong pattern might mean violent dynamics, extreme anisotropy, or a sudden injection of degrees of freedom. A live code could survive local insults. Error correction is built for that, but fail gracefully with signatures. Small symmetry-breaking alignments, low-L anomalies, directional preferences, and effective couplings. Not a crash, more like a recoverable glitch that leaves scars. Now, if gravity is emergent, G is an effective spring constant for spacetime's elastic response. In entropic gravity pictures, the pull we feel is a gradient in information density. Change the information energy map and the spring changes. Screening mechanisms, where extra fields hide their influence in dense regions, look less like conspiracy and more like a feature. The code is stiffer where data is thick, looser where it's thin. That would reconcile quiet labs and talkative intergalactic gas without magic. It also frames moaned-like regularities in galaxies as emergent relations in a particular phase. Low acceleration regimes reveal the code's long wavelength elasticity. Meanwhile, holography isn't our universe's exact language. ADS isn't the sitter, but the grammar travels. Entanglement wedges, reconstruction, islands in black hole evaporation. Each step shows that geometry answers to information. If that's true broadly, then the dark sector can be reread. Dark energy as a state counting effect, a pressure from finite code capacity. Dark matter as emergent quasi-particles of the underlying microtheory, sometimes condensing, sometimes free. In such a world, constants are metadata, stable most of the time, context-sensitive at the edges. Here's a human beat that grounds the abstractions. A young researcher spends months trying to make a simple boundary deformation produce a tiny bulk anisotropy in a tensor network. Nights blur, the code keeps breaking. One morning the network stabilizes, just barely, and the bulk geodesics lengthen by a fraction in one direction. It's artificial, small, and fragile, but it's a controlled knob that turns geometry. The group laughs like people who have been underwater too long. They don't claim a universe, they claim a lever. What would count as evidence that emergence isn't just a metaphor? Correlated drifts. If alpha, some lensing amplitude, and a low L alignment all lean in the same direction on the sky, matching a pattern you can derive from an information flow model, that's a fingerprint. If lab clocks tie tight bounds locally while astrophysical absorbers see a spatial tilt that tracks large-scale structure, that's environment talking. If early dark energy helps H and simultaneously looks like a transient change in the code's redundancy, visible as specific polarization phase shifts, then we're past poetry. And falsification matters. If next-gen CMB and lensing maps crush the allowable space for early pulses, if clock networks and quasar spectra refuse to agree on any directional drift, if G and labs converges while galaxies keep their moan-like line but superfluids fail their predictions, then emergence retreats to the blackboard. That's fine. Emergence earns its keep by making concrete, testable ties between information and force. The promise isn't mystical, it's practical. Treat laws as summaries of deeper organization and you get new handles, error-correcting robustness that explains why physics is stable, plus failure modes that explain why it sometimes is. A living code doesn't mean a coder. It means dynamics that build order from many parts. If that's our cosmos, then the glitches aren't mistakes. They're messages about how the code breathes when it's pushed. The experiments that could break it open. If the code is alive, we need experiments that don't just refine plots, they corner reality. No more near misses, no more consistent with. The next wave aims for tests that can't be explained two ways. Start with the new eyes on ancient light. The Simons Observatory is about to flood us with polarization maps sharp enough to see the faint swirl imprinted by matter between us and the CMB. CMB S4 will push even deeper, knitting thousands of detectors across the coldest, driest places on Earth into a machine for reading acoustic fingerprints. If early dark energy left a pulse near recombination, these maps should see it as tiny phase shifts in polarization peaks and a lensing amplitude that lands in a narrow, predicted window. Miss that window, and a big chunk of the patch notes theory collapses. Hit it, and we've got a smoking signature that links H's disagreement to a real change in the early rulebook. Meanwhile, we'll weigh the expansion from both ends with spectroscopic giants. Daisy is already turning galaxies into rulers, mapping baryon acoustic oscillations across a huge span of cosmic time. Euclid is scanning broad and deep, combining weak lensing shear with redshift surveys to track structure growth and geometry together. Roman will tighten supernova distances and add lensing statistics with a wide, crisp view. Together, they hand us expansion and growth in stereo. If the sound horizon truly shrank, bow distances at high redshift will line up with a shortened ruler, while the growth history won't tolerate cheats. If the ruler is fine and the latter is biased, the stereo picture will refuse the edit. But we also need judges who don't use the CMB ruler at all. Enter gravitational waves, standard Sirens. When two neutron stars collide, their waveform gives you absolute distance, and if you catch a host galaxy's redshift, you get H without ladders or ancient sound. LIGO, Virgo, and KAGRA have a few. A next observing run with better sensitivity could deliver dozens. Add next-gen detectors and a lucky bright electromagnetic counterpart, and a 2% H is realistic. If that number sits with Planck 67, the latter must answer. If it joins the 73 crowd, early universe fixes earn a second look. If it splits the difference, the mystery deepens and the field will feel it. On the ground, the clock network becomes a cosmology instrument. Tie strontium in Boulder to ytterbium in Tokyo to aluminum in Paris with stabilized fiber links, and you're not just keeping time, you're measuring whether alpha's ratios tilt together, anywhere on Earth at the same moment. If a dark field rolls by like weather, ratios across continents should twitch in sync, with a sky-dependent phase. No lab can fake that pattern alone. Fly one optical clock to space, on a quiet platform with thermal stability your basement can't match, and compare it live to the ground. If screening hides variation in dense environments, the space clock might see a slightly different effective alpha than the one below, a clean A/B test on the environment hypothesis. Pulsar timing arrays add another ear. Millisecond pulsars tick like nature's best metronomes, and networks in Europe, North America, and Australia now hear a background hum from supermassive black hole binaries. That's one win. Next, subtle deviations in those tick patterns, after subtracting the hum, could betray long wavelength fields that couple to clocks or gravity. It's a long shot, but it's complementary. If a scalar field drives a slow drift, pulsars give us a sky map of its phase and amplitude, free of lab systematics. Then there's the 21-centimeter frontier. Neutral hydrogen's spin-flip line traces the fog before and during the first stars. Experiments like Hera and later, the square-kilometer array will map this glow across cosmic dawn, giving us a time-resolved view of how the first structures grew. If early dark energy tweaked the expansion near recombination, the timing of heating and reionization shifts subtly. Cross-correlate 21 cm maps with CMB lensing and galaxy surveys, and you get a triangulation that either allows a brief early pulse or strangles it. We haven't forgotten gravity in the lab. Atom interferometers are scaling up, larger momentum separations, longer baselines, and heavier source masses to push down systematics. Portable devices now measure tiny gravity gradients. Array them and you can watch mass move in real time. If G hit an environment dependence at parts per million levels, a calibrated network could sniff seasonal or loading-linked modulations beyond known tides. Most expect a null. That's the point. A hardened null prunes entire classes of scalar tensor games. And because we've been burned by pretty anomalies, these projects are building skepticism into the plumbing. Blind injections in data streams. Split, firewalled analysis teams that only meet at the end. Cross-instrument checks where one group gets to pick the calibration set for the other. A Daisy redshift bin that's also a Euclid shear patch, and a Roman supernova field becomes a stress test. 3 instruments, 1 sky, no excuses. Here's the human part that makes all this more than hardware. Teams are promising each other in writing what counts as a pass or fail before the plots exist. If the polarization phase shift is outside this band, we drop this class of early dark energy. If 3 clock ratios don't co-vary within this template, we stop calling the quasar dipole physics. It's uncomfortable. It's necessary. While the data loads, you can feel the room lean forward. Either the ruler was misread or the code really did flicker. Either alpha hums with the sky or it holds. Either gravity is a constant we haven't measured cleanly, or it's a response that changes with context. These experiments won't be polite. They're built to force a choice. The human chain of doubt. While the instruments get sharper, the real calibration happens in people. Doubt is a relay, passed hand to hand at 2 a.m., in emails with too many attachments, in Zoom windows where someone finally says, "Run it blind." The stakes aren't abstract. A bad claim can freeze a young career. A careful null can be a decade well spent. The field moves because people risk being wrong in public and then keep showing up. Start with a small moment that doesn't make a press release. 2 rival teams, both chasing the same lensing signal that could tilt S8. They meet in a shared Slack channel late at night and agree to swap calibration files, PSF models, shear biases, star catalogs, without the answers attached. No names on the files, no clues about which pipeline is whose. A week later, they compare. Both numbers shift by less than a hair, but in the same direction. The trust that buys is worth more than the shift. It says, "We'll let you touch our guts because the result matters more than the scoreboard." Confirmation pulls hard. You spend months cleaning an effect, and it's human to want it to survive. That's why the best groups build self-sabotage into the method. Blind offsets and parameters. Hidden sign flips in intermediate steps that only get removed after the paper draft is written. It's not theatrics, it's armor against the brain's urge to steer. A postdoc who's convinced they see an early dark energy signature watches the unblinding erase half the effect. The room goes quiet. The advisor nods and says, "Good, we didn't fool ourselves." You also see the other end of the arc, a paper rejected twice that changes the conversation years later. An analysis of quasar absorption lines gets dinged for calibration risk and ambiguous systematics. The authors take the hit, build a new pipeline that models isotopic shifts directly, and release all their code. The result is no longer a clean dipole headline. It's a landscape of possibilities with clear flags where the data's honest and where it's speculative. It doesn't settle the argument, it reframes it. Suddenly the conversation is about which isotopic priors are defensible, not about whether someone made a mistake. That's progress, in the slow tone the outside world rarely hears. The grind is semesters of nothing. A graduate student measures clock ratios week after week, finding only the building's heartbeat. Their plot is flat and beautiful, no drift, just noise that keeps shrinking. They learn that a null, when it fences what's allowed, is a brick in the wall, not dead air. Across campus, an interferometry lab fights a vibration at 17 Hz that shows up like clockwork. 3 months later, they tie it to a ventilation fan on the roof. They fix it. Their G measurement doesn't leap to match the competitors. It moves by a fraction of a fraction. Still, the lab cheers like they won a prize. There are public costs. A senior figure posts a bold preprint claiming a resolution to the Hubble tension. Media outlets leap. Within days, independent reanalyses show a hidden prior that tightened the error bars. The author posts a correction, then another, and then a sober follow-up that admits the prior drove the conclusion. It hurts. It also models the only right move. Own the mistake, explain why it happened, and give others the tools to avoid it. Younger researchers notice. The field hardens in a way that's healthy. The most important debates aren't competitions, they're design reviews. Think of the meetings where teams define what would count as evidence before the data comes in. If gravitational wave standard Sirens land at 71 with 2% error, we agree to treat early pulses as alive. If polarization phase shifts miss this narrow band, We retire this family of models. Writing those sentences feels like locking doors before you know what's on the other side. That's the point. Pre-commitments keep theory from stretching to fit any outcome. They protect the question. Micro-stories stack into culture. A programmer leaves a comment in a pipeline. Here be dragons. This mask amplifies eclipticaline junk, and 5 other teams copy the warning into their code bases. A junior collaborator speaks up in a meeting to say their lensing weights correlate with seeing conditions more than expected. The plots lose a sliver of precision when corrected, and everyone thanks them instead of grimacing. A referee report arrives with a demand for a split analysis the authors dread. 3 months later, the split reveals a subtle bias, and the paper is better for it. There's a phrase that keeps showing up: duty to kill your favorite idea. It's harsh, but it's a compass. In private, people love their models. In public, the job is to hand them to opponents with a smile and say, "Break this." That's how you protect wonder. Not by softening edges, but by inviting attack. When an idea survives that, it feels earned, even if it's provisional. So what happens if the glitch is real? The culture we've built is the only one that can handle it. The same habits that make us suspicious of pretty plots, blind pipelines, cross-instrument sanity checks, pre-declared thresholds, are the ones that will let us say, without flinching, something moved. And if the constants hold and the tensions were our fingerprints, we'll have learned how to erase ourselves from the data more cleanly. Either way, doubt is the chain that keeps us honest, while we tighten the bolts on reality. 3 scenarios if the constants move. Scenario 1, subtle drift, the quiet fixable universe. What it looks like: constants like alpha or the electron-to-proton mass ratio slide by parts per million over gigayears, and by parts in 1018 per year locally. Lab clocks see nothing but ever tighter nulls. Quasar absorbers and 21 cm maps see a gentle, redshift-dependent slope. G in labs converges. Gravity at cosmic scales stays within lambda CDM with a small early time edit. Physics story: a light scalar field rolls slowly and couples weakly, screened in dense environments, active in the intergalactic medium. Early dark energy, like pulses, were real but small, just enough to shave the sound horizon without breaking lensing or S8 beyond repair. Consequences: navigation software, GPS, finance timestamps, no changes today. Metrology updates standards with a paragraph about environmental sensitivities. Astrophysics gets refinements. Stellar opacities tweak by a hair. Nucleosynthesis yields shift in the second decimal place. Molecular cooling in early clouds slides timelines by 1%. How we'd know. Clock networks continue to return hardened nulls locally, but long baseline quasar many multiplet analyses with web-class stability show a consistent ppm trend with redshift that survives isotopic modeling and laser comb calibration. Val plus SN plus standard Sirens triangulate an H that sits between Planck and the latter, with early polarization phase shifts just inside the allowed band from Simon/CMBS4. No coherent sky pattern, just time dependence that matches a rolling field prediction. Scenario 2, Anisotropy, the directional universe. What it looks like: constants are stable in time where we sit, but not the same in all directions. The fine structure constant is higher by a few ppm in one hemisphere and lower in the opposite. The pattern aligns loosely with large-scale structure, not with the ecliptic or galactic plane. Labs stay quiet, the sky hums. Physics story: environmental coupling. A scalar field's vacuum expectation value responds to matter density or cosmic shear, with screening in dense regions. The field's spatial mode imprints a dipole or low-L texture across our Hubble patch. Gravity's effective spring could also vary slightly with environment, nudging lensing amplitudes directionally without wrecking clusters or the CMB. Consequences: astronomy adjusts calibration playbooks. Absorption line studies report direction with the same seriousness as redshift. Lensing and shear analyses include a low-L template marginalization tied to structure maps. Avoid zones becomes practical, not fearful. Precision experiments that are environment-sensitive get scheduled or oriented to minimize bias from known anisotropy patterns. Cosmological parameter fits gain a column, isotropic versus anisotropic posteriors, with priors that penalize solar system, aligned templates to kill local systematics cheats. How we'd know. Independent instruments, VLT espresso, Keck HIRES with combs, JWST/NIR spec, recover the same dipole in alpha using disjoint absorber sets and explicit isotope modeling, surviving blind splits and sky rotations. CMB, large-angle anomalies and weak lensing maps show a low-L alignment consistent in phase and amplitude within uncertainties, not explained by foregrounds or scanning strategy. Local optical clock ratios remain null, while a space clock shows a tiny offset relative to ground that modulates with pointing through gravitational potentials, matching screen coupling predictions. Scenario 3, phase shift, the regime chain. What it looks like, a real time-bound change in the rulebook, an early universe phase where an extra energy component or coupling turned on and then off, left multiprobe fingerprints. The Hubble tension doesn't soften, it snaps to a side with standard Sirens. CMB polarization peaks show specific phase shifts. Lensing amplitude lands outside lambda CDM's comfort band even after aggressive systematics control. Some late-time probes hint at a mild departure in growth history that bin-by-bin reconstructions can't absorb with priors. Physics story. A field crossed a threshold near recombination, Z~300-500, briefly altering the sound speed or adding a few percent energy density, then quenched. In gravity language, the informational code stiffened and relaxed, an honest physical patch note. This isn't drift, it's a localized epical edit with knock-on effects in structure growth and lensing. Consequences. Cosmology textbooks get a new chapter, Lambdictum, plus, with a documented early time pulse and its parameters. The standard ruler's provenance changes, and bow analyses adopt the shortened sound horizon with updated covariances. Astrophysical inferences that depended on the old ruler, ages, distances, halo masses, get recalibrated. Not a calamity, a version update. Theory focus swings. Model building shifts toward concrete, UV-safe fields that pass BBN and lab bounds, but still generate the required pulse and polarization phase signature. How we'd know. CMB S4 and Simon's Observatory detect polarization phase shifts and a lensing amplitude in the narrow window predicted by early pulse models, inconsistent with pure lambdictum at high significance. Dozens of bright standard Sirens with host redshifts deliver H to ~2% and pick the same side as late-time ladders or Planck plus EDE fits, closing the triangle. Dacey, Euclid, and Roman produce bow plus SN plus growth constraints that remain mutually consistent when the shortened ruler is adopted, while S8 tensions don't worsen beyond forecasted trade-offs. A fourth, rare outcome sits in the margin, catastrophic mismatch. That would look like correlated failures across clean, independent probes, clock ratios twitching globally in sync with a sky-tide pattern, CMB polarization off-template, lensing geometry and galaxy flows disagreeing even after brutal systematics campaigns, and standard Sirens refusing both rulers. That's the calamity case. A true breakdown of our effective descriptions in a way that demands new organizing principles, not patches. It's unlikely. It's precisely why we're building experiments that can tell clever errors from real edits. What it means if the code is alive. If the ratios twitch and the rulers argue, maybe we've been reading a living document and calling it law. A code that adapts isn't chaos. It's a system with rules that depend on context. That sounds slippery until you notice how often physics already works that way. Temperature changes phases. Density changes behavior. Scale changes what counts as a particle and what counts as a field. We've just been lucky that most of our world sits in a quiet patch where the rules feel carved into stone. So what changes if the code is alive? First, humility stops being a slogan and becomes a method. Laws become best-fit stories we tell about stable regimes, not commandments. That's not defeatist. It's how we've always won. Electromagnetism in circuits, fluid dynamics in pipes, quantum fields in colliders, general relativity in GPS. Each is a slice that holds because the system sits in a phase where the slicing makes sense. When a boundary is near, low accelerations in galaxies, recombinations pivot, ultra-cold clocks staring at the floorboards of time, the edges show. Second, meaning gets a new shape. People want the universe to mean something. Physics doesn't write purpose into the sky, it writes pattern. A living code gives you a different kind of meaning, resilience. If constants are stable because they're protected by structure, error-correcting redundancy in the way information arranges, then stability itself becomes the message. We exist because the code is robust enough to carry chemistry, stars, and memory through noise. That's not a cosmic plan. It's a property of systems that learned, by dynamics, to keep their shape. Third, responsibility shows up. If rules adapt to environment, then changing environments, on Earth, in orbit, in deep space, becomes a way to ask the universe questions without waiting centuries. You don't just observe, you probe. Build clock networks and you're not just keeping time. You're testing whether the electromagnetic font thickens or thins with potential. Map lensing and shear with sharper eyes and you're not just weighing mass. You're measuring how the gravitational spring responds to emptiness. The lab and the sky stop being separate. They become a single instrument. There's a human consequence too. Certainty has been the most dangerous constant in this field. It blinds you right before the turn. A living code keeps you honest because it keeps moving the goalposts a millimeter at a time. The right stance isn't cynicism, it's curiosity with guardrails. Pre-commit to what counts as evidence. Invite attack on your favorite idea. Celebrate nulls that fence the map. That's how you don't waste a decade on a mirage, and how you don't miss a real drift hiding at the edge of sensitivity. Does a living code demand a coder? No. Emergence doesn't need intention. Snowflakes tile without a designer. Ant colonies route traffic without traffic laws. Black holes count their bits without a clerk. If spacetime and fields are the macrostates of deeper microdynamics, then alive means responsive, not conscious. The system can have failure modes without malice and corrections without mercy. That's scarier and more beautiful than any tidy story. A universe that stabilizes itself most of the time and leaves room, at the margins, for the surprising. If you follow that thread, you start to see why the glitches matter even if every single one turns out to be an artifact. The process we've built to interrogate them, blind pipelines, cross-instrument checks, shared calibrations, predeclared thresholds, is exactly the machinery a living code demands. It's how you separate your fingerprints from the ink. It's how you listen for a moving target without chasing noise. Even when a glitch dies, the instrument we built to kill it survives and hears more. And if one of these whispers holds, then the story gets richer, not smaller. A subtle spatial tilt in alpha tied to large-scale structure says environment talks to electromagnetism. A lensing amplitude that refuses to sit with Planck says the gravitational spring softens or stiffens with context. A clean standard siren H that picks a side says the early universe ran a patch we didn't write down. None of these trash physics. They add a chapter. Here, S the regime where the code breathes. There's also something personal in the idea that laws are stories. It gives you permission to leave room for wonder without sacrificing rigor. You can say, out loud, that you don't know whether early dark energy is a mirage or a memo from recombination, and that not knowing is the honest place to stand. You can build instruments designed to embarrass your own model and call that love for truth, not betrayal. You can teach students that their job isn't to defend a canon, but to test how far a story goes before it bends. The last shift is practical. If the code can move, the most valuable constant we can cultivate is vigilance. That means designing systems, technological and social, that can update quickly without breaking trust. In tech stacks, that looks like versioning the physics in your navigation software if clocks ever see a drift. In science, it looks like open data, reproducible pipelines, and a culture that rewards careful reversals as much as flashy claims. If the universe is allowed to change its mind, we need to be allowed to change ours. So when you hear constants, don't hear granite, hear tempo. Most of the time the beat is steady. Sometimes a bar stretches. If we're lucky and careful, we'll be there with metronomes and maps catching the stretch as it happens. The meaning you can take from that is that the universe cares. It's that it's legible, stubbornly, beautifully legible, even when the script edits itself mid-performance. And our job is simple and hard: build better ears. Resolution and broader meaning. The most dangerous constant is certainty. It blinds us right before the turn and makes us miss the quiet edits in the code. If you want the next chapter when fresh data hits, Simons, Dacey, Euclid Standard Sirens, subscribe and watch the companion deep dive on early dark energy right after this. Share this with someone who still thinks constants don't argue back, and let's keep testing the rulebook together.